Welcome to Part 10, the final one of this series of talks on drillstring and drilling dynamics. It's devoted to lateral dynamics, specifically the lateral dynamics in horizontal and high-angle wells. Simple models of drilling tubulars either regard them as cylinders, or as cylinders with additional masses and pivot points at the joints, which is an idealized model of a drill pipe. Most of this presentation will use drill pipe models, though it will be partly about cylinders, as this helps explain and motivates the drill pipe examples. The lateral dynamics of tubulars in horizontal wells is different in the two directions, vertically across the well and horizontally rolling from side to side in the well. I'm going to start with the dynamics of a periodic pin beam, which is a model for the vertical deflections of drill pipe where the tool joints stay in contact with the bottom of the hole. Then I shall move on to the dynamics in the other direction, where it is rolling from side to side in the hole, firstly for cylinders and finally for drill pipe. First, the pinned beam, which is a model for drill pipe with tool joints that sit periodically on the bottom of the hole, in the case where there is no compression or tension. First, the static solution. This was covered in the 8th presentation on bending and touch points. Ignoring the gravitational bending of the pipe between the touch points, the deflection is a cubic, which is 0 at the touch points, here -1 and 1. We look for solutions which are periodic or exponential. The result is a decay of 2 minus square root 3 between sections and a sign change. It looks like this. The pipe has been given a twist at -1 and is pivoting at the odd numbers. Each section looks the same, but scaled and sign reversed. Incidentally, if you are modelling a BHA and want to model infinite drill pipe at the top, this is the boundary condition to use for vertical deflections. Let's add dynamics by looking at non-zero frequency. We will start with the solution for a constant cross-section beam. As is well known, the 4 linearly independent solutions to this may be split into 2 evanescent solutions, ones which decay exponentially, and 2 propagating harmonic solutions. The wave number is proportional to root frequency, which means that the wave number goes to 0 at 0 frequency. We can perform the same analysis as for the static case for the periodic fixed points using the dynamic solutions, and end up with a formula with lots of harmonic and exponential functions in it. If we look at that half lambda plus 1 over lambda formula versus k, the wave number, we get an oscillating curve. It goes to -2 at the origin, which is the static solution. Over various intervals, it is between -1 and 1, and there it is the cosine of an angle. Where it is more than 1 or less than -1, there is exponential decay between sections. This is exactly the same phenomenon of pass and stop bands we saw with propagation through periodic pipe for axial and rotational waves, with 2 important differences. Whereas for axial and rotational waves, there is a pass band at 0 frequency, for this vertical lateral motion, there is a stop band. Also, the x-axis here is the wave number in the cylindrical sections, which is proportional to root frequency, not frequency, as for axial and rotational waves. All that was for uncompressed pipe. Now we can add compression, or tension. Unsurprisingly, it gets a bit more complicated. This is the simple, constant cross-section beam. The propagating and evanescent wave numbers are different, but both tend to the same high frequency limit, which is the same as the wave number without axial load. There are 2 evanescent solutions and 2 propagating solutions. If the beam is under tension, the wave number of the propagating solutions goes to 0 at 0 frequency, but the evanescent solutions have non-zero wave number at 0 frequency, so static solutions decay over distance. Under compression, the 2 are reversed. The evanescent solution has 0 wave number at 0 frequency, whereas the propagating solution has non-zero wave number at 0 frequency, which is the buckling instability. Here's what the different situations look like for wave number versus root frequency. No axial load and a straight line. For tension, a lower wave number growing sublinearly, For compression, a finite intercept on the y-axis. And now, of course, the same analysis for periodic fixed points. And again, a formula for cosine of the angle across one period. The cosine of a one-period phase change against root frequency, showing no axial load, and also the effects of some compression and some tension. At high frequencies, they all merge, but at the origin, with tension there is more decay from one section to the next, with compression less decay, and the width of the first stop band is correspondingly wider or smaller. If there is enough compression, then the stop band at zero frequency disappears. The pipe will undergo static buckling. That was all for dynamics vertically across a horizontal hole. But what about in the other direction, side to side? We start not with pipe with joints, but with cylinders. For the dynamics, I am only doing a linear analysis. The extra term in the equations is the lateral restoring force, due to gravity and possibly any curvature present. Just as when there is no cylindrical confinement, the solutions split into pairs, which I have labelled with P and E, because in the high frequency limit they tend to the unloaded, propagating and evanescent solutions. The very low frequency behaviour depends on the sign of T squared minus 4FB over R, which you may remember from the static buckling discussion. Tension first. If the tension squared is high enough, it is just like the unconfined case, a propagating solution and an evanescent solution with a finite wave number. However, for low tension, there is no real propagation. All the solutions decay with distance, but with varying phase as the wave numbers are complex. For compression, low compression, like low tension, has no propagating solutions. Whereas for compression above the Dawson-Paisley limit, there are propagating solutions with finite wave number at zero frequency, which is the buckling instability. That's all at close to zero frequency, but what happens a bit above that? Take a look at the governing equation again, but in the frequency domain. Clearly something interesting happens when the right-hand side is zero. This is the rolling resonance for the cylinder. There is a zero wave number solution, which corresponds to the cylinder undergoing simple harmonic motion from side to side in the hole. Although this is very obvious when you look at the right equation, I first found this doing numerical simulations and couldn't work out why I had a BHA resonance that didn't vary with BHA length. If you're in a deviated straight hole, then this rolling frequency can be at a typical pipe rotation speed. For most parameters, the frequency at horizontal is higher than normal rotation speeds, which means that for most horizontal wells, somewhere in the drillstring, there is a section that is rotating at close to this resonant frequency. It's difficult to believe that this never has any consequences. Looking at the whole frequency range, for a cylinder in tension, it is fairly simple. Solution behaviour always depends on whether the frequency is above or below the rolling resonance. Below the resonance, there are no propagating solutions. Above it, the normal situation of a pair of propagating and a pair of evanescent solutions re-emerges. This is an example of what wave number versus root frequency looks like. Propagation at small wave number starts at the rolling resonance frequency. What about when there is compression, but below the Dawson-Paisley limit? There are now 4 different situations. If the frequency is close to zero, no propagating solutions. For frequencies above a limit, which goes down with increased compression, but below the rolling resonance, all the solutions are propagating. At the rolling resonance exactly, there are 2 propagating solutions and 2 zero wave number solutions. And finally, above the rolling resonance, 2 propagating and 2 evanescent solutions. An example of what this looks like for a compression a fraction of the Dawson-Paisley limit. As the compression increases, the position of the front of the nose moves towards the y-axis, finally touching it at y equals 1, at which point the red line, going back to 0 on the x-axis, disappears. This is what Dawson-Paisley looks like in the frequency domain. At zero load, The first propagating frequency is the rolling resonance. As the load increases, the position of the first propagating frequency moves down until it hits 0 at the Dawson-Paisley limit. That was cylinders. Now, finally, rolling pipe. The difference between rolling pipe and rolling cylinders is that it is not the pipe but the joints that are rolling in the hole. The pipe between joints doesn't have any contact, so the equations satisfied between the joints are the equations for pipe under axial load. It is the boundary conditions at the joints that have the rolling condition, and since the joints are moving, there is also inertia. At lower right, I have written down what the static vertical force looks like at each joint. It has a gravity term, the weight of the whole pipe length. The distance between joints is here 2L, and also a curvature term that depends on the relative height of the joints in front and behind. If there is positive curvature, this term will be positive, negative curvature, and it will be negative. If we look for periodic or exponential solutions, and write the half lambda plus 1 over lambda combination as x, then the resulting equation to be solved is the top equation. The solutions are written below. Let's take a very simple case first. Vertical hole, no tension or compression. There are two pairs of solutions. I'm not going to look at the evanescent solutions, just the ones closest to being propagating. This is cosine of the phase across one period. The curve almost snakes back and forward between 1 and -1. There are tiny stop bands with small attenuation when it hits the boundaries, which come from the inertial effect of the mass of the tall joints. Now, the rather unrealistic situation of a horizontal hole under 20,000 pounds of tension, obviously not possible without something holding the drill bit. You could see that just as with the cylinder, there is no propagation until the rolling resonance frequency is reached, shown by the vertical dashed line. After that, the phase changes very fast with root frequency, and the next stop band, at root frequency of just over 2, is virtually non-existent. Same situation, but no tension or compression. Very similar behaviour. Again, the first stop band is tiny. Now, some compression is applied, 20,000 pounds again. Propagation now extends below the rolling resonance frequency, just like it would with a cylinder, but an appreciable stop band appears just above it. So compression that we have come to expect means an increase in the ability of lateral waves to propagate actually has the opposite effect just above the rolling resonance. I think it is clear that the propagation of bending waves in rolling jointed pipe is quite complicated. There are a lot of parameters here, and I encourage those interested to see how they affect the dynamics. So finally, a summary. For both horizontal pipe and collars, there is a cut-on frequency for propagation of bending waves. This frequency comes down as the compression increases, reaching 0 at the Dawson-Paisley limit when sinusoidal buckling is initiated. Horizontal pipe has a pass and stop band structure for bending wave propagation, which can be complicated. Whatever the compression, there is always a rolling resonance, and when drilling a high-angle hole, somewhere in the string will be rotating at the rolling resonance. All of this must be relevant to horizontal drilling, though I'm not sure exactly how. There is always lateral excitation of the drill string at the rotation speed due to small, non-axisymmetric mass variations, and also at double the rotation speed due to the combination of stiffness variation and gravity. Whether these vibrations propagate, resonate, or are localized could have important consequences for vibration levels, and also associated issues such as cuttings movement and steering effectiveness. That's it, the end. If anyone has watched all 10 presentations, I hope you have found the time worthwhile. A contact email is on every slide. Please feel free to contact me on the subject of the presentations, even if it is just to tell me about typos or mistakes.